welcome to SciLux, the podcast where we talk about scientific developments and technological changes in Luxembourg. Of course, as usual, proudly powered by Research Luxembourg and recording at the Media Center of the University of Luxembourg. And in today's episode, our guest is Alex Tkatchenko, who is a professor of theoretical condensed matter physics at the University of Luxembourg. He is also head of the Department of Physics and Materials Science and head of the Theoretical Chemical Physics Group. His research pushes the boundaries of quantum mechanics, statistical mechanics, and machine learning to develop efficient methods to enable accurate modeling and new insights into complex materials. He has also received 5 flagship grants from the European Research Council. Alex, thank you very much for coming today.
Thank you, and thank you very much for the invitation.
I have to say that we did not discuss it before, but I will definitely have to ask you how to call this episode, because we can't call it physics. Chemical physics will not describe it. The problem of journalism is always we are limited with the number of characters, because I think we're going to discuss a lot of different things today, right? Because this is also in the sentence that I introduced you with. You're really touching upon so many different domains. So we start with the last one I had the chance to actually listen about, so the dark energy part. So I don't know how many of our listeners had the chance to be at the lecture, which was very interesting, at least for me. I could not follow everything, I have to say, but I was trying very hard. You were talking about dark energy and vacuum, right? So there is something about computation to understand the dark energy. So what are you up to?
So the origin of this goes back to Einstein, so more than 100 years ago. And Einstein elaborated his general theory of relativity that aims to describe space and time and gravitational phenomena that we see around us. And after he did that, he wanted to explain how the universe works. So what happens to the universe? Is it static? Is it contracting? Is it expanding? And in order to do so, he had to realize that the only force that dominates the evolution of the universe, which was known at the time, was gravity. And gravity is an attractive force. So things tend to collapse. So if you have, solar systems and they interact with each other, they tend to collapse. And so if you look at those equations, you would first think that everything would collapse in the universe and you would come to what is now called a big crunch. And so in order to not do that, because back in those days, it was actually thought that the universe is static, so it has a fixed size, he had to introduce a new term in his equation, and that's called the cosmological constant. That just means that the free space, the vacuum, has a certain energy. Very, very little energy, right? It's extremely small. Orders of magnitude smaller than any energies that we work with on Earth. However, it turned out Einstein thought that this term could actually make the universe static. Unfortunately, that was not completely true because the equations are very complicated. And I think this will come back in our conversation a few times, that the equations, I think, are more beautiful and more intelligent than the humans that write those equations. Because once you write the equations, you don't understand the implications of those equations, actually. And that happened exactly with this general relativity equation of Einstein applied to the universe. So the implications of those equations are very, very many, and they were not understood at the time. So it turned out that you can throw away this cosmological constant term and you can still produce a static universe. And so because of that, Einstein decided to throw away this term. But then Hubble, who is another very important part of this story, Hubble was doing astronomical observations and he observed that the universe is expanding. And he convinced Einstein that this was true. And the only way to then explain this was to basically get back the cosmological constant term into the equations. The whole story, of course, is much more complicated than I'm saying. But this cosmological constant term was coming in and coming out. And Einstein didn't like it very much. And he called this the greatest blunder of his career. because, how can you keep adding and removing things? In principle, in physics, you shouldn't have the freedom to do so. But so that term is there. It's now well accepted. It has to be there. But at the moment, no one knows how to explain it. And that's where my work started. So I, as a chemist, well, not a chemist, but let's say someone who works on quantitative sciences, trying to bridge physics, chemistry, and biology, I'd like to calculate things from first principles. I like to calculate values, not just understand the concepts, but actually make predictions, make quantitative predictions. And before my work, this was not done yet.
If I may, I'm just wondering, but then theoretical physics is not about calculating, is it? It's more about coming up with the theory.
There are different branches of theoretical physics. I think that what is called high-energy physics or cosmological physics is often about inventing new concepts, inventing equations. But when you apply those equations to something realistic, like the planet, the solar system, the galaxies, the universe, oftentimes, if there are measurements that give certain values, you should be able to predict those measurements. And that's where even theoretical physics, I would say, becomes actually quantitative science.
But coming back, you wanted to calculate it. And what did you do so far?
So I started with something that people have done for a long time. So if vacuum has energy, vacuum means absence of matter, by the way. So in physics, we have particles and we have fields. These are two fundamental objects of physics. And everything we see around us are particles. So we are used to think of particles. But in empty space, there are no particles. So what is there in empty space? There are fields. And those fields are not empty. They are quantum mechanical. So nature is quantum mechanical. And because they're quantum mechanical, they change their space-time all the time, right? We call in physics, they fluctuate. And in materials, those fluctuations yield many different types of interactions. And so my idea was, what if we apply the same idea to fields, to calculate how fields interact with themselves? Would that lead to a prediction, to an energy that you could compute and that will be finite and that you can compare to experiments? And it turns out you can. You construct a model, you calculate the energy, and it turns out that this energy, which we call the self-interaction energy, actually matches the astronomical observations of the cosmological constant. And that was a big surprise. And in fact, I didn't start doing this exactly to compute the cosmological constant, but it turned out that was the prediction.
And this is a very interesting point to say, just like you said with the cosmological constant, is that Einstein put it there assuming that the universe is static, right? So very often in science, it is somehow a byproduct of chasing something else that you end up with a result, right? So now that you have this, what's next? I guess talking to the experimentalists is...
There are several things that follow up. I cannot predict the future. I mean, I'm working on several different directions at the moment to extend this theory. Next things, there are many so-called tensions in cosmology and observational astrophysics. For example, there's a tension that says that these energy density have actually evolved from what is called the cosmic microwave background, which happened 300 million years after the Big Bang until now. And we are now about 14 billion years away from the Big Bang. And so recent observations, just in the past 2 years, actually, have converged to the idea that actually those energies have been different. They evolved. And there are, again, many theories that tell us why they could evolve, but they don't predict the actual values of that evolution. And so that's one step that I'm taking as well, and to predict those values and to see what is the mechanism for this evolution of this cosmological constant in time. And then there are many, many, many other questions that follow from.
Of course, oversimplifying it, but in general, why do we need to understand dark energy?
On our scale, tables and our bodies and so on, they don't depend much on this, on the dark energy. But in the end, the same situation happens with all other progress in science. So the general relativity of Einstein is just, for example, a generalization of Newton's law. And on Earth, And for many things that we do every day, understanding Newton's law is enough. But actually for GPS, for example, technology, you cannot rely on Newton's law. There are general relativistic effects that come from the unification of space-time that affect the functionality of GPS system. And so it's the same applies to every progress in physics, right? When lasers were developed, no one knew what we would use lasers for. And I think one can follow this thousands of examples where any progress in our fundamental understanding can lead to technologies and many other improvements and maybe also problems in our lives.
And that's the beauty, to use again this word, of fundamental science, I guess, right? This is really that kind of being very much in the dark, not to use a very bad pun on dark energy, and then finding something that can apply to so many different fields. So great to hear that. And you mentioned chemistry part, so I want to look at it very soon. But before we do that, you also mentioned space-time. So we have to talk space and time. And I know that you prepared 2 pub quiz questions for our listeners. Yes, I'm letting him ask 2 questions, listeners. I just had to go for both of them because both of them are very interesting. And remember, the answer only at the end of the podcast.
Right. Thank you, first of all, for allowing me the 2 questions. And the 2 questions come because there is space and time in physics, and we cannot take one without the other. And so I thought I would ask 1 question about space, 1 question about time. So the question about space is, well, we just discussed that the universe is expanding. This is a fact. And so it means that everything flies from everything else. So distances increase between objects. So does this mean that our galaxy is being slowly destroyed? Does this mean that our bodies are expanding as the universe expands? Or is this false? The second question is about time, and this is a very short question. Does physics allow traveling in time?
Great questions, a bit sci-fi, the travel in time. So I'm always for it, totally. And as I said, I already hinted at it. We are looking a little bit now at chemistry. So I just wanted to ask you, okay, we have the dark energy part and space and all the research you're doing, but also, of course, we have physical chemistry, right? So you focus on that and on quantum chemistry. So first of all, what is going on in the field of physical chemistry? And is it like mornings for physical chemistry and afternoons for space research, or how does it work for you?
So I would say that at the bottom, everything is actually connected. So I'm trying to understand how the laws of quantum mechanics apply to complex systems and understand the emergence of new phenomena. When we make our systems bigger, more complex, what do we find? What is the novelty in it? And once again, this beauty comes up because it turns out that you write the equations are always the same. Now it's just Schrödinger equation. So for chemistry, everything is in a Schrödinger equation. And well, there's also statistical mechanics because you have to understand how atoms move around. But in the end, the basic is the Schrödinger equation. So the Schrödinger equation is extremely simple. But looking at the equation doesn't tell you anything about the system that you are looking in. Be it a molecule, for example, we know that we can predict how drugs function in our bodies, starting from quantum mechanics. This is possible, right? All we need to do is to solve the Schrödinger equation and run the dynamics with the forces that we obtain from the Schrödinger equation, and we would understand everything about drugs functioning in our bodies. But that requires understanding systems with billions of atoms. And it turns out that at every scale, so you start from small molecules like water, you have 3 atoms, right? H2O. You find new phenomenology, you find new emerging interactions. Then you look at how water molecules interact with each other to form ice, or to form liquid water, or to form water surfaces. And you find every time new and new phenomena. Now, the equations you are solving are the same, but they lead to such a beautiful phenomenology, which is extremely complex. So today, I would say, we know the basics. It's quantum mechanics, it's statistical mechanics. We then use machine learning to accelerate all those computations as well. But once we do that, I would say that what we are doing is not quantum mechanics and statistical mechanics. We are doing science of molecules. We are doing science of materials. We are doing science of space and time. So the equations we are using are all the same. So I think in my own work, of course, I have to split my time in terms of thinking about molecules, thinking about materials, thinking about space and time and fields. Nevertheless, the fundamental concepts are the same. They don't change. And so there's a lot of unification underlying all those different fields. And I think that's very important also to communicate to the audience and to younger people that studying the fundamentals is perhaps the most important thing, because you can actually study anything. You can study chemistry, physics, biology, material science, if you understand the fundamentals.
And this leads me, of course, to the education at school. I have to mention that. What do you think? Why is there still this kind of silos approach on studying biology, studying physics, and not having of chemistry, and not having this cross-disciplinary approach? Because this is the way to go. We both agree.
We agree. I'm not an expert on education. I think education is a very important topic. It's a very difficult question whether what people have, what students have to learn from their primary and secondary school. I do think that, for example, quantum mechanics cannot be taught in school because they're missing the mathematical apparatus that you need in order to understand and to apply quantum mechanics. You need linear algebra, you need differential equations, and that's something you usually do not really touch in school. But the concepts underlying quantum mechanics, I think, can be explained to a teenager. There's nothing magical about them. Well, actually, there's a lot of magical things about them, but you can actually explain it with normal language. And actually, that's where I think that schools could be a bit more creative in having experts who can communicate science, who could actually explain to students how creative science is and how beautiful it is and how magical it is. And I think that's a bit missing in the current education. My own children go to secondary school. And of course, I can see that. And I think I went through secondary school. I think it was not very different.
That's a good point. Although I have to say that I keep going back to this point that in my school, the secondary school, they showed us the beauty and the creativity of mathematics. But only mathematics, I have to say. There was nothing with physics. Honestly, I did not see the beauty that I see right now. And as you're saying, I think this is also a question of being mature, educated enough to understand certain concepts. But there must be something about the way it is taught too.
Right. I think it also depends on the teachers. Every teacher has a different approach. I have to say, actually, something interesting that in my own career, so I was always fascinated by computers growing up. I grew up in the 80s, 90s, so that was where everyone wanted to become a programmer. And that's what moved me. My parents are mathematicians, so I did have a good mathematical education, but I never really thought that mathematics is fun. I thought you need it. So, and that was enough, right? You need to understand that you need mathematics. And I would say you really need mathematics, right? This is the basis for every science, at least quantitative science. But then, only when I started my university education, I was actually impressed by physics and chemistry because of professors that were teaching it. And they explained things in such a way, they just made you question, for example, what is friction? Right? Just asking what is friction and then explaining that you can predict it from interactions between molecules and atoms in your shoes and the earth on which you are walking. And just thinking about that, this changed my mind. Because I wanted to predict these things. And can I calculate this? Can I understand it? Can I form my own picture? And that's I think, this simple phenomena that you see on every day. Once you realize, well, they are not magical, you can predict them. And then this becomes magic for you, right? That you can actually predict such things.
So going back to the magic, as you mentioned, some of it, of quantum mechanics, you mentioned the Schrödinger equation. And I was just thinking that maybe not everyone knows what it is. So we should probably explain it first.
At which level?
Your listeners, can you tell us which level you want? I think if you can water it down as much as possible would be amazing.
Right. So everything in physics starts from classical mechanics. So this is what we learn in school, Newton's theory. So in that theory, everything, all objects that we observe, they usually have mass. And so we can exactly pinpoint every object. So we can define its position and its velocity. And then objects interact. For example, if you look at solar systems, planets interact with each other and they orbit the sun, which is the most massive object in our solar system. And the same happens, with all the other objects in classical mechanics. So you can actually look at every separate object one by one. And you know exactly where it is and what is its velocity. In quantum mechanics, this no longer holds true because you have to think of a wave function, which is a field for each object. And so each particle, electron or proton, would live in its own space. But these objects also interact. And so now, basically, in many body systems, so a system of many particles, like an atom with many electrons, would live in a very high-dimensional space, and each particle would interact with all the other particles. So in order to understand how each particle moves, we need to know everything about all the other particles. So effectively, if you have now n particles, we are living in this 3 times n dimensional space. And that's what makes it very complicated, because you have to work with these extremely complicated objects, but you cannot separate them, right? And that leads to very, very, very interesting phenomena, of course, and to the complexity of quantum mechanics.
And that's what Schrödinger equation is about.
And the Schrödinger equation predicts, it gives you a way to compute the evolution of the system in time, essentially.
You mentioned the n particles, so I just have to go into that direction. How many particles have we discovered and how many do we still need to discover? Because I have a feeling that I kind of, don't read the news and once in a while I miss yet another new name for a particle that someone discovered or assumes there might be.
So there are in physics, in high energy physics and in a so-called standard model of physics, which describes all particles and all fields, it's pretty settled. So we know what are elementary particles and we know what are the fields, but all of them interact. And that leads to new phenomenology as well. So sometimes you have composite particles. So for example, a proton or a neutron in atoms are composite particles. They are composed of quarks, and quarks are the fundamental particles, right? And so from the point of view of fundamental particles, sort of the standard model and high energy physics have been, I would say, it's maybe a wrong expression, but it was kind of killed by the discovery of Higgs boson, because it kind of was the missing piece of the standard model. And with that, one can say the standard model is over. It might not be true, because you can still find new particles, and people are building larger and larger synchrotrons to smash these particles and find new particles. But in the end, we are restricted by the size of our Earth. And so at some point, we will not be able to go further and further and further to higher energies and find new particles. And the interesting thing is, in chemistry and material science and condensed matter physics, we know what the particles are. We only care about electrons, protons, neutrons, sometimes positrons, because we can create positrons. And in fact, they're used for medical imaging, for example. But those are all the particles we really need. Well, maybe muons as well. They're used for probing certain things. But those are all the particles we need, and we know what they are, and we can actually calculate what they do, to a certain material or molecule or protein.
This also leads me to the question I wanted to ask you. So if you talk about the chemical molecule, this is basically the limit that you look in. You don't go deeper for the particles. Or am I mixing something here?
So we start with particles. Those particles, so electrons, positrons, neutrons, protons. And that's all we need to set up our calculation, right? And then we know the system that we are working. And so we don't need to go to find new particles. We need to go and understand interactions between those particles when there are many of them. For example, say you have a protein, right? How does it fold? No one knows. We can predict folded structures today using machine learning, but we don't know how proteins get there. So that's kind of things that we can actually do, and that we are developing the technology and the science to actually do that kind of question.
Why do you need to know how proteins fold?
Well, because biology is all about dynamics. Biology is not about static structures. Static structures are very important because they allow you to start asking certain questions, but biology is fluctuating. Our bodies are constantly changing. Proteins in our cells are evolving. They have chemical reactions. They have mechanical response, and all of this is connected. And all of this is very dynamic.
When you look at proteins, I guess you have to choose one that you focus on in your work. It's not that you can have a model for all of them. So have you focused on a special type of protein in your work, and what was it?
Yes. Again, you start from the ground up. Like in high energy physics, you start from elementary particles. For proteins, the elementary particles are secondary structures. They are helices and beta sheets that form proteins and loops as well. So first, what we did, and this we did already about 10 years ago, is looking at how quantum mechanical interactions affect structure formation of helical peptides. So alanine, which alanine is an amino acid which is very widely used, of course. And so we wanted to understand the balance of different interactions that go from the unfolded structure of this peptide to a folded structure. And there are actual experiments that ask exactly the same question. And so we could show that we have a predictive theory to explain why peptides fold and how they fold.
And why do they fold?
Because there is a balance of interaction. So peptides, proteins, are in water, usually. And so there's a balance between the internal stabilization of proteins via interactions. And there are many different kinds of interactions. There's a whole jargon, whole field. It's called hydrogen bonding interactions, van der Waals interactions, electrostatic interactions, and so on and so forth. It all comes from the Schrödinger equation, by the way. If you solve the Schrödinger equation doesn't tell you, oh, this is a hydrogen bond. Oh, there is a van der Waals interaction. Oh, there's an electrostatic interaction. No, it's all in there. But in order to interpret, scientists elaborate these ways of calling things names. And it's like a closet, right, where you open, different, or like a table, you open different drawers, and you say, oh, this is a hydrogen bond. Oh, this is an electrostatic interaction. Oh, there is a van der Waals interaction. But it's very important. That's what we do. And by providing these different categories, we could say, well, 20% of stabilization comes from hydrogen bond, 50% comes from van der Waals interactions, the rest comes from the electrostatics. And by doing this, it allows us to understand how many different proteins would fold, because we can control those effects. And then, people do experiments, we compare the experiments, and that's how science progresses.
And that's when it comes to proteins, but you also look at different materials. So like polymers, probably. Do you apply your theories to polymers too? Or
we don't directly work on polymers, but biological proteins are polymers, right? They are biopolymers. And so, yes, indirectly we can do this. We actually have an ongoing project looking at what is called polymer melts, which are very, very big systems with millions of atoms. And what we are trying to do there is to develop new science, new equations, new methods to actually be able to handle millions of atoms. At the moment, with our methods, we are able to handle tens of thousands of atoms, which is enough to actually look at small proteins in water. But we want to go to millions of atoms. And because that's where biology, you can actually do biology. And so that's something we've started to develop. And we first look at polymers because polymers consist of simple molecules, right? Simple molecular building blocks. And so that's one application that we are looking at.
Okay. And there's also one of the projects that you're involved in, which is, faster drug development. Is that related, or is this yet another approach?
It's all related, as I said. In the end, the equations are the same, but the way that you address different questions and different systems is a bit different because, of course, whenever you ask a question, for example, how drug binds to a protein, that means you need to understand small molecules. Drugs are small molecules. And how do they basically fit into the pockets of a protein? So this kind of brings together our two different expertise because we've worked on molecules for a very long time. We started working on proteins about 10 years ago, and we are bringing these two things together. And also materials is also a question that I've been working on it in the past, actually before I came to Luxembourg. I continued doing a bit of it. I have a project now on battery materials, for example, to study how lithium ions diffuse through a material. So basically how to design a material where you can optimize lithium diffusivity. But it's exactly the same question, right? It doesn't matter if the atom is carbon or if the atom is lithium. The beauty is it's the same equation.
And we go back again to the word beauty. So, I was planning to touch upon this because I have to say that the recent book I'm reading on physics is a lot about beauty and a lot of questions of why do we always discuss this? So I need to ask you too. You did mention it a couple of times. So it seems to be an important factor for equations. So what is beauty for you and why are we discussing whether an equation is beautiful or not?
I don't think, an equation can be beautiful.
You don't think it can?
No. So the beauty in physics is usually this. So once you discover a new phenomenon, for example, if you take Maxwell's equations. So Maxwell's equations describe the electromagnetic field. If you look at the original work of Maxwell, it's a mess. I think there are 20 equations and they look horrible. But then Einstein came and he unified those equations through unifying space and time. And suddenly you get just more beautiful equations because you unify them. And then quantum electrodynamics came and they worked with other objects. And then the equations become more compact and compact and compact. And this equation becomes just, 3 symbols together. Now, of course, each symbol means something very complicated. But if you can write something in 3 symbols and simplify it to that, and of course, physicists understand what those symbols mean, then it's beauty. Because you don't have to write the 16 equation. So I think that's the beauty in equations. But there is a beauty in science, which I think is more fundamental when you actually do in science. So why we talk about beauty is because it feels like when you make a progress, for example, when you make a prediction, just on a computer, right? So you wrote the theory, you implemented it on a computer, you ran simulations, you predicted something. And of course, you have to be very humble because most predictions are wrong. But once in a while, it turns out that then people do experiments and they confirm your prediction. And I think the feeling you have is a feeling of beauty. It transcends, yourself. It transcends even, Earth. It's something more fundamental. It's beautiful, right?
Yes, for you. No joking. I'm just thinking about all the listeners who, when they see an equation, they run away because there are people like that as well. So it very much depends on what your specialty is. But I would tend to agree with you for sure. But I was also thinking somehow recently, whenever I have philosophical discussions, then it's mainly with physicists. Is there some affinity between philosophy and physics? Do you suddenly turn into philosophy when you do physics? Do you feel that? Or is it just the small sample of physicists I know that like doing philosophy?
I think that this is correlated to the age of people to whom you talk.
Possible, yes.
So when I studied physics or other disciplines, I was not thinking of philosophy very much. And I would say I even kind of despised it, being not a natural science or quantitative science. But as you grow and as you become more interdisciplinary, and as you start talking to your colleagues in very different departments, humanities, social sciences, engineering, you start realizing that there's an underlying line of thought that is very similar. And of course, philosophy is that line of thought, right? Because we are using principles, and those principles are philosophical principles. And it turns out also in physics, many concepts that we work with have philosophical meaning, right? And so I think knowing philosophy, especially philosophy of science, is actually very important. And I have to say that I faced this because actually my wife studied philosophy. She did a master's degree in philosophy of science. And many of her courses were taught by natural scientists, mathematicians, physicists, chemists, and also by philosophers and by social scientists. But confronting and discussing with her, I realized that, it's not very different. It's science in the end. And it's just that in physics, we prefer not to stay at that level, right? We really need to write an equation. We need to solve the equation. We need to falsify our predictions with experiment. And so we rely on empirical evidence. And if our theories are beautiful, but they don't stand empirical evidence, we have to throw them out.
We went very far away from the thing I mentioned in the very beginning, which is ERC. And I don't know how to bridge the gap between philosophy and ERC right now, because we're getting very concrete into grant space. But I have to ask you, of course, because, you're one of the star grant getters in Luxembourg, I would say. So we said 5 already from ERC, and of course a lot of from FNR as well, a lot of different funding happening. But I wanted to focus on ERC in this case. Any suggestions to people who are actually toying with the idea to apply for a grant? What has been your experience? Because there is a lot in here when it comes to experience with ERC.
I've seen it from all sides. So I've been, of course, applying for ERC. I've been getting ERCs. I've also been in the reviewing many ERC grants. I've been on the committees, on ERC committees, panels that evaluate those grants. And so first of all, I don't think there is a rule of thumb. I think many grants, even the ones that are successful, they follow very different trajectories. So when a person tries to think, okay, am I eligible to apply for a grant? So I think one needs to be very humble and also basically ask people around in their groups, in their universities, but also prominent people in their field. And just to, have an opinion. Usually in science, I would say most people are nice. Some people are less nice, but most people are nice. And they actually like to give advice. Right? That's how scientists, that's why we teach. We give advice to younger people. So you can always ask people, am my background, am my track record good enough? How good is my idea? That's another thing which is important. So you shouldn't hide your ideas. I think you should discuss your ideas with as many people as possible. I know that this doesn't work for all fields. For example, in very competitive fields, people do not like to disclose their ideas because many other people might have the same idea at the same time. In my career, I found that it's actually better to just openly talk about ideas. And just see what other people think. Does this make sense? Doesn't it make sense? And many people will maybe tell you it doesn't make sense. But if you just find a few that do find it appealing, then perhaps it's worth pursuing. Right? So I think there's two things, right? So first of all, for ERC, you need an idea, right? I mean, everything is based on some idea. It has to be a novel idea. And so you need to make sure that this idea is good. And to do so, talk to as many people as possible. And I think that's also something that people don't realize or realize very late is that science, also natural sciences, quantitative sciences, actually a very social enterprise. It's as social as any other, as politics or business. It's talking to your peers and not only your immediate peers, but also a bit far away from your field. Is something you need to do when you want to apply for ERC grant, for example, or any other, bigger grant.
Why people don't realize that it's also social?
So many people study natural sciences because they don't like writing and they don't like interacting with other people. They don't have, very prominent social skills. But this is something you can learn. And I think it's very important to learn it from very early stage. And I think this should be repeated more than it is done now. That from a very early stage, it's okay to be an introvert, but you still need to be able to interact with other people and talk as much as possible and not enclose yourself, right, into your own little, playground.
And I would add to it, of course, from my field, a small appeal as well. Then you also have to go out and tell the public about what you're doing, because this is also something we're missing. The communication about your projects. And this means that I have to thank you very much for accepting my invitation today to tell us a little bit, because it's very much a little bit. I don't think we really went deep in any of the fields, but I'm sure, listeners, that if you're interested, you will find all the information online about Alex and what he's doing. Go to some of the lectures or any other place where he is present. And this means only last thing that remains are the pub quiz questions that we have to solve. Of course, I will not leave you without the answers. So if you can remind us what the questions were and then what the answers are. We take it step by step. So let's start with the first one.
Okay, so the first question was about space. So space expands. This is a fact now. And if space expands, is everything expanding? Do the galaxies expand? Are the distance between planet and our planet and sun expands? Do our bodies expand? So for that, in order to answer this question, we need to understand that there are different kind of interactions in the universe, in physics. And the universe expands because empty space loosely, quote unquote, expands. And that means that the distances between objects in the universe is expanding. But inside galaxies, what dominates is not the expansion, but it's actually the gravitational attraction. And so inside galaxies, nothing is expanding. Galaxies are still there. They will still be there for another billions of years at least. And the same applies for planets. Our Earth is not expanding. Our bodies are not expanding. And even if you imagine flying on a rocket, Elon Musk rocket maybe in the future, into the empty space, far away from our galaxy, your body will still not expand, even if you are in a vacuum, because in your body, you have other interactions. You have electromagnetic interactions that keep your cells together. And so you will still be okay. You could still survive in completely empty space outside of any galaxy.
Yeah, you probably know that space is one of my interests. I don't know whether you'll be completely okay because you probably have to also breathe and eat and other things. But from that perspective, for sure, yes. Okay, so we have the space part and now we have the time part.
Yes, so the time part, the time question was, does physics allow traveling in time? There is no easy answer to this question. But in many subfields of physics that we know, time travel is perfectly allowed. So in classical physics, in quantum physics, even in field theory, actually you can time travel because time is simply a parameter. You can go back, you can go forward, you can redefine zero of time anywhere. And so you can actually travel in time. This is not a problem. The problem comes when we turn to other subfields of physics, as thermodynamics, for example. And thermodynamics introduces this concept of entropy. And the concept of entropy introduces what is called an arrow of time. So we can only go in one direction in time, but we can still time travel. Thermodynamics doesn't. We can go only in one direction, right? So maybe we cannot return, but we can go forward in time. So it's interesting that in physics, there's not one defined concept of time. Actually, physicists, and this is connected to of course, philosophy, as you correctly say, are still discussing what is the nature of time. Is time real? Is time emergent? Or is it something completely different that we don't know of? So I think that is what makes actually physics so fun to do. Because things that we mention every day, time, space, we actually don't know what these concepts are.
And that's why sometimes it's also problematic when I ask seemingly simple questions. I remember I asked your colleagues, Massimiliano Esposito and Emanuele Pennocchio were here, and I asked them exactly about one of the laws of thermodynamics. And I thought, well, they would just give me a definition, like 2 sentences, and that's it. And they started discussing for a long time, actually, how to formulate it so it's clear, but also where are we with the agreement? So it's very interesting because, of course, school has to serve you a simplified version where there's no doubt. They will not tell you, well, this is the theory you need to learn, but we are still not sure there. Imagine if you were learning about time in physics classes and then you were actually knowing that people still don't agree what time is, right? I mean, this would really make it very difficult to study. So, but it's an important point. And I also wanted to mention that as you're talking about time, I had an interview about time perception, which is also very interesting because that was from a psychological point of view, of course. And, then, of course, we were not discussing what time is, but how we perceive it and how subjectively we perceive it is very, very interesting too. So I'm leading the listeners also to that conversation if you're interested in that. And what remains is to thank you very much for 2 of your pop quiz questions and the whole discussion. It was very, very interesting, Alex. Thank you so much.
Thank you again for the invitation.
And that's it for today. Don't forget to subscribe, to follow us, to read what we are writing on all the social media, suggest guests or questions. We are always open for new ideas. This was Silax, and my name is Hanna Siemaszko.